I wish to introduce Dr. Vogel, who's kindly agreed to talk to us about Fraunhofer FEP. That is one of the many Fraunhofer institutes, in this case, concerned with organic electronics and electron beam and plasma deposition. And the obvious question to start with, Dr. Vogel, is what is all that? How does it fit together?
Okay, thanks for the good question. And indeed, considering the history of Fraunhofer FEP, originally it was founded in 1992 or so, and long before my time. And at that point in time, it was mainly dedicated to electron beam and plasma technology. So mainly methods for creating or for generating electron beams and for performing specific, let's say, material, adaptation steps, but also, let's say, for using electron beam, let's say, for different kinds of applications, as for instance, also, let's say, sterilization, also for, let's say, for electron beam based evaporation, and several approaches. And plasma technology has mainly been used for deposition of several materials, thin films, for instance, also barrier films, but also, let's say, optically active films, or let's say for optical filters or similar. And let's say these two general topics have been the original reason for founding these institutes in the early 90s. The organic electronics actually joined Fraunhofer FEP in 2014, and since it was until that point in time, it was part of another Fraunhofer entity, which has been joined with FEP in 2014, and that's why, let's say, now it's organic electronics, electron beam, and plasma technology. But anyway, one of the reasons to join, let's say, these, or let's say, this organic electronics Fraunhofer entity together with the original Fraunhofer FEP was that there have been, let's say, several synergies already before that. So we already had some collaboration with Fraunhofer FEP, for instance, also on their expertise in, let's say, in specific tools and specific equipments. So, for instance, also, let's say, in OLED, but also, let's say, in thin film deposition in general, there are sheet-to-sheet equipment as well as roll-to-roll equipments, and Fraunhofer FEP, already the original one, has been active in developing roll-to-roll tools, for instance, for barrier film depositions. And at the previous Fraunhofer Comet, which worked in the organic electronics, we already operated a tool for OLED roll-to-roll deposition, which was already before 2014 located at the Fraunhofer FEP, but operated by Fraunhofer Comet at that point in time. And also, let's say, Fraunhofer FEP originally has been rather, let's say, process development oriented, whereas the previous Fraunhofer Comet has a little bit more focus, which was focusing on organic electronics, but more focusing on using processes, also developing processes, but also using processes for specific applications. So, for instance, for displays, for micro displays, or also for OLED and lighting and signage applications. So, and that made also, let's say, a good fit for Fraunhofer to even, let's say, make use or make advantage of the synergies between the process-oriented original FEP and the more, let's say, application and product-oriented or device-oriented Fraunhofer Comet, and so that synergy turned out to be successful.
Well, that's interesting. And organic electronics, sometimes that includes inorganic materials and composites on an organic substrate, or are you specializing specifically in organic active materials?
Well, in the in the FEP in general, we are working on several types of substrates. So, I mean, of course, we make use of organic substrates. For instance, also barrier films are being deposited on organic substrates, for instance, by roll-to-roll processing, and those foils are being used for packaging, for instance, packaging applications or other applications. We are also making use of glass substrates, obviously, both rigid as well as ultra thin glass that can be flexible. And also, let's say, ultra thin glass, for instance, can be used for both as a substrate as well as an encapsulation, let's say, material again, so to provide barrier properties, for instance. So, and last but not least, if we consider micro displays, we are using silicon wafers, single crystalline silicon wafers as a substrate, where we deposit the OLED on top, on 8-inch wafer level, for instance. And also, let's say, the OLED becomes covered with a thin film encapsulation layer again, with a barrier layer, and also, last but not least, with a hard coat or with another color filter, glass wafer or similar. So we work with several types of substrates, and often we heterogeneously combine several materials, inorganic, organic, with each other.
Yes, and what you put on them is also organic and inorganic,
yes,
like
yes,
the barrier
yes.
layers. Do you do the duplex ones with the organic and inorganic layers?
Yes, that's one thing. Or the organic semiconductors themselves, which are, well, organic. But for instance, also for optical filter layers, these might be inorganic materials again. So,
all right.
And often these are also, let's say, combinations of both.
All right. And your speciality is micro displays. Can you tell us a little more?
Yes, sure, of course. So micro displays are, well, usually very tiny displays, typically screen diagonals less than 1 inch, but even more typical, these are, let's say, 0.2 inch, 0.4 inch, 0.6 inch. So rather tiny displays, and you always need some sort of optical magnification to perceive an image out of those tiny displays, since you have to imagine that on such a tiny screen you still have the same number of pixels as you have on a regular, well, nowadays, mobile phone display, TV screen, or whatever. So very tiny, and you would not be able to, let's say, to perceive an image with your naked eye from such a tiny screen. So you always would need some optical magnification in front of that, and that optical magnification could mean, let's say, virtually, or let's say, a virtually enlarged image. So you have some sort of magnification optics that projects the display image into, let's say, your natural field of view. This can be augmented reality, or this could be virtual reality, or maybe also an electronic viewfinder where you have the same, let's say, projection setup. Or it can also be, let's say, a real, let's say, enlarged magnification, so like in a projector, for instance, or in a front projector. So, but in any case, let's say some optical magnification is part of that, and so always you have a tiny display and a much larger image perceived. And we also make use of OLED, so organic semiconductors again, for making those micro displays, OLED micro displays, obviously in that case. And the technology for that is called OLED on silicon. So we use a single crystalline silicon wafer substrate. We perform the so-called backplane design. So if you think of such a micro display with millions of pixels, full HD resolution, for instance, so each of the millions of pixels has to be addressed and driven and controlled individually. So you need a backplane for that, an active matrix backplane, similar as you have it in a mobile phone, but whereas in a mobile phone, you have a thin film transistor backplane. In micro displays, we use a single crystalline silicon backplane. So much more compact devices, much higher performance, but a much smaller area. And we make this IC, integrated circuitry backplane design, so the pixel array circuitry, and let's say also surrounding driving and control electronics. And then we receive the wafers from a wafer fab, so we send our design data to them. We receive the 8-inch wafers from that fab, and then we perform the OLED post-processing in our line, in our pilot manufacturing line. And then we come up with such tiny displays. Maybe I can even show you something.
Yes, yes. Of course, OLEDs have been a huge success and a long way to go, haven't they?
Is that something that can be seen here? I don't know. It should light up inside. Can you see that? There should be some.
Tiny.
Well, yes, that's the idea.
Absolutely.
And
yes,
I
yes.
can even show you the display itself.
Yes.
I mean, most of that is just battery, electronics, and the tube.
Yes.
And the tube over here is mainly hollow. And there's a lens in front of that, and the actual display is here on the end of this tube. So you can imagine that's the interface towards the display. So it's a serial interface, so just a few cables inside, and the display is here behind that tape. And so the display itself is, I don't know, about 3 by 4 millimeter, or let's say the entire chip is about 3 by 4 millimeter in size.
Yeah.
So, and the display area maybe about 3 by 2 millimeters, and that's it, so rather
What
tiny.
sort of applications are now envisaged?
Yes, I mean, specifically that sort of display is intended to be integrated into, let's say, near-to-eye displays.
Yeah.
So let's assume you have kind of sports glasses, and you have such a tiny display. I mean, the optics is, as you can imagine, the biggest part of the entire thing.
Yeah.
But there are also different optical solutions you can think of.
Yes.
And then you can really integrate that, or at least the display and the interface for that, let's say, into the nose frame of a,
Yes.
let's say, of spectacles. And then you might also consider, let's say, a different type of optics that is more or less, let's say, also projecting the display image onto let's say, your eyeglass. And then you would also embed some maybe smaller batteries in here, and also, let's say, electronics, the same as here maybe, but also in a smaller form factor that provides a Bluetooth low energy connection to your mobile phone, for instance. And then you can wear that, let's say, during cycling, for instance, during bicycling, or let's say also during professional activities, and you perceive additional information. Let's say in a semantic context to the activities that you are currently performing. And let's say, and the eyewear device itself is a rather thumb device. It's just a display, the optics, of course, and let's say a wireless interface. And then let's say all the processing power and cloud connection and whatever you might need could be performed by your smartphone, for instance.
Right.
So that is, and what is specifically important, let's say specifically in those wearable applications, is obviously battery life. So I mean, you would not like to recharge your device every 4 hours or whatever. So let's say during cycling it should last at least 1 day, and independent if it's 12 hours or 8 hours or whatever. And that's why we, let's say, also this specific micro display architecture has been developed to really, let's say, achieve ultra low power consumption. So, I mean, finally, the power consumption of that chip is just related to those pixels that are on at a certain point in time. So, and all the other pixels are off, but the major difference to, let's say, to regular OLED displays on the market is that even the chip itself does not consume much power. On a regular, let's say, micro display nowadays, the chip would consume power even if the display content would not change. So, and to give you, let's say, a proportion, let's say the backplane, the chip itself would consume about 150 milliwatt, but there would be no change in the screen content. So even, let's say, if the screen would be completely dark, all pixels off, it would consume this 150 milliwatts, so actually for nothing. So, and then of course the actual OLED, the power consumption for the OLED emission comes on top, whatever, 10 milliwatt, 50 milliwatt, something like that. And for that architecture, even if you display a certain screen content, the chip itself is not really consuming power. It's much less than 1 milliwatt that goes into the chip. So it's almost about a factor of 100 between a regular display backplane architecture and this one. So as long as there's no change in the screen content, you just consume the power of the OLED pixels that are on and that are emitting light. So and the chip itself is more or less consuming nothing anymore, and that really improves the battery life of such a wearable.
Yes,
and
yes.
significantly,
So,
not
yes.
just a few hours.
Yes,
So now you
yeah.
can talk about days, weeks.
Yes, yes. So there were companies that were unsuccessful in this field many years ago, weren't there? So these advances should make the product a commercial success. That's very exciting. Well, you have a remarkable virtuosity in your institute, so thank you very much. We shall stay very close to you. You're extremely impressive in what you're doing, and thank you very much for talking to us.
Thank you as well for, let's say, this kind interview.
You're welcome.